let's go ahead and try applying our notions of stability and buckling now to the case of the buckling of beams. So this is sometimes known as Euler buckling. And so let's consider a beam that we are applying an axial load P to, and we'd like to figure out at what load P does the system buckle. So this is like the demos that I did a little bit earlier, but now we're going to do the actual calculation to figure out at what load does the buckling deformation occur at. So the way we're going to do this is, so this is the state that we're going to try and figure out, and the way we're going to do this is we're going to write down the equilibrium equations for the system and then look at the solutions of those equilibrium equations and look for the appearance of secondary non-trivial solutions. So let's go ahead and cut out a differential element from the buckled shape of the beam, and we'll take that as length delta x, and now let's put on all the possible loads onto the system. So first of all, there's possibly a distributed load on the system. Then we also will have the internal shears at both faces, so V of x and V of x plus delta x. We have the moments on the two ends of the differential element, so m of x and m of x plus delta x. And lastly, we have the axial force on the system, and the axial force is going to be P, acting through the center of rotation at each end. So notice that the two values of the axial force, they're offset by the amount of deflection that I have from one end of the differential element to the other. So V of x plus delta x minus V of x. So let's go ahead and write down the equilibrium equations. So if I write down the sum of the forces in the vertical direction, I have minus V of x plus the contribution from the distributed load, so that's integral from x to x plus delta x of q of x, plus the vertical force on the right side, so V of x plus delta x. If I go ahead and use the usual construction, divide through by the size of the differential element, and then take the limit as the size of the differential element goes to 0, I'm going to find out that I get dv dx plus q equals 0. So this is exactly the same equation of equilibrium that we had before when we looked at beam problems, so nothing changes here. So let's go ahead and look at moment equilibrium of the system, and I'll go ahead and take moment equilibrium about the center of rotation on the right side of the system here. So we'll take it about this point right here. And so I have the moment from the left side, and I'm taking positive counterclockwise, so that I get a minus sign here. Then I have the moment from the right side here, so that's m of x plus delta x. I'll have the moment due to the shear force on the left side, so that's V times the lever arm, so V delta x. And then I have the moment due to the distributed load. And let me go ahead and simplify things here. I'll go ahead and replace the distributed load by a single point force right in the center, and I'll assume that is q delta x in magnitude. So that's an approximation. But then the lever arm here is just delta x over 2. So that gives me this term here for the contribution from the distributed load. And then I also have the contribution due to this moment over here, or this force, and that acts through a lever arm of, which is the differential distance of deflection from the left side to the right side. So V of x plus delta x minus V of x. And all of that has to sum to equal 0. So I can go ahead again, divide through by delta x, and take the limit as delta x goes to 0, and I get dm dx plus v plus p dv dx equals 0. So we have the shear force v and we have the deflection v. So lowercase and uppercase, so you have to keep those straight with each other. And you notice that the distributed load q doesn't appear in this relationship here. And so that's why I was a little sloppy with how I accounted for the moment due to the distributed load, since I knew it was going to drop out. You can do it a little bit more precisely, but you end up with the same result. So this is the moment equilibrium equation, and the first equation here is the force equilibrium equation. If I want, I can combine them as I have done before, and also make note of the fact that the moment is equal to EI times the second derivative of the deflection, so EI times the curvature. If I put those all together, I get a single differential equation of equilibrium for the beam here. So EI, 4 derivatives of V, assuming EI is a constant, plus PV double prime equals Q. So it's almost the same as what we had when we computed deflections of beams, except for I have this additional term here that is the axial force times the second derivative of the deflection. Okay, so that's the new term that I have in my equilibrium equation. So let's go ahead and try and apply this to a particular problem. So this is the pin-pin case. We've seen the demonstration of this, so we know what it does when it buckles. It pops out sideways when we apply a sufficient amount of load, but if the load isn't too large, then it just sort of stays in its position. So in this particular case here, I have no distributed load, so Q equals 0, and the boundary conditions are no deflection and no moment at x equals 0, and no deflection and no moment at x equals L. So that's the setup here, and I want to look at now at the solutions to the equilibrium equation. So my equilibrium equation in this case looks as follows. There's no Q in my system. And I'm going to have to go ahead and solve this using sort of classical techniques of ordinary differential equations. Because I have two terms here, if I didn't have this second term here, I could go ahead and just integrate this 4 times. But because of this second term here, I'm not able to integrate in such a simple fashion. I actually have to solve the differential equation using classical methods. So the classical method is to assume an exponential form. So v of x is some parameter or constant a times some unknown parameter, or that times the exponential of an unknown parameter s times x. And so if I plug this form into the differential equation here and then divide out the e to the sx, I'm left with ei s to the 4th power plus ps squared equals 0. So this is known as the characteristic polynomial, and this allows me to determine what these parameters s are in my assumed functional form. So if I go ahead and solve for s, I have 2 roots which are 0, so s equals 0, plus or minus I times the square root of p over ei. So these are the 4 roots of my characteristic polynomial. And so the general solution then can be written as follows. So first of all, the imaginary roots are going to lead to sines and cosines, and the first 2 terms will lead to a constant term and a linear term. So put all together, I have this general solution to my homogeneous differential equation. So v of x is equal to some constant I'll call a1 times the cosine, plus a2 times the sine, plus a3 times x, so that's the linear term, plus a4, which is the constant term. So for each term that I pick off from any of my roots of my characteristic polynomial, I'm going to have a different coefficient a. So those are just standard solutions to differential equations, and this is the homogeneous solution to the differential equation. There's no particular solution I have to worry about because the forcing term is 0 on my differential equation. Okay, so we can now try and use the boundary conditions to determine what the constants a1, a2, a3, and a4 are. So if I go ahead and look at the boundary conditions at x equals 0, I find out that a1 plus a4 equals 0 from the deflection condition. And then the moment condition tells me that minus a1 times p over ei is equal to 0. So that second term immediately tells me that a1 equals 0, which if I look back at the first condition then tells me that a4 equals 0. So a1 and a4 are going to disappear from my solution here. Now if I look at x equals L and evaluate the deflection condition, the moment condition, I end up with these 2 relationships here. If I look at the second of the 2, I'll notice that combined with the first, that's going to tell me that that a3 has to equal 0. Okay, so if a3 equals 0, then what I'm left with is a final solution of v of x is equal to a2 sine of the square root of p over ei times x, where I'm left with still the second condition here, which says that a times the sine of the square root of p over EIL is equal to 0. So this is my equilibrium solution to my system, and it has this unknown parameter a. Notice that if a equals 0, I'm going to have a trivial solution. So what I'm really interested in are the conditions where if a2 equals 0, I'll have a trivial solution. And what I'm really interested in are the conditions on the load that will allow a2 to be non-zero. And that's going to come out of this second equation here. If the argument of the sine function allows the sine to be equal to 0, then a2 can be non-zero, and I can have a non-trivial motion or buckling of the system. So just summarizing, so a2 equals 0 is the trivial non-buckled or unbuckled case of the system, but when the square root of p over ei times L is equal to any integer multiple of pi, then that sign here is going to be equal to 0, and a2 can be non-zero. Okay, so I end up with a sequence of discrete values of p where I can have non-trivial motion of the system. So just solving this relationship here for p, I get p is equal to j squared, where j is the index, the integer index on the multiple of pi, pi squared ei over L squared. The critical value of the system is going to occur at the minimum of this sequence of values of p, and so that's going to be for j equals 1. That's going to be the minimum, so I get what's known as the Euler load, pi squared ei over L squared. So that tells me when that beam is going to buckle, and the shape that's going to buckle into is going to be a sine wave. So I can see that right there. That's the eigenfunction to this differential equation here. So this is the basic setup here. There are a number of common cases that are useful to know. The one that we just solved for is the pin-pin case. That gives us what's known as the Euler load, pi squared ei over L squared. Different boundary conditions give you different loads, as we saw in the demonstration. So this is the pin clamp case. That was the other case that I demoed for you. And if you go through the analysis with these new boundary conditions, namely the clamp boundary condition here at the bottom, you find a result that's just slightly over 2 times the Euler load. So just changing the boundary condition, making it a little stiffer, increases the buckling load by approximately a factor of 2. Other common boundary conditions are the clamp-free case. So in this case here, the critical load, if you apply or determine it using these boundary conditions, so namely free at the top and clamped at the bottom, you get 1/4 of the Euler load. And the other common case that we have is the clamp-clamp buckling case. So if I restrain the top of the beam from rotating while I apply an axial force while it's clamped at the bottom, I end up with a critical load that's 4 times the Euler load. And so each one of these results here comes from using the appropriate boundary conditions for the geometry of the system at hand. One thing to be careful about when you do these types of buckling calculations is that the bending can occur about multiple axes. And so if the boundary conditions are the same in both directions, so say bending about the y or bending about the z axis, so let's go ahead and let's say that's x, and then y, and the z axis is coming straight out at us. So you can have bending about the z axis, which in this case here would go like this, or you could have bending about the y-axis where the beam would bend out towards you. Okay, and so what you need to do is make sure when you're evaluating the buckling load, there's this moment of inertia, and you need to use the minimum of the two. So you have the bending moment of inertia about the y-axis, and you have the bending moment of inertia about the z-axis, and you need to pick the minimum of those two values when calculating the buckling load. Now, the boundary conditions can be different for buckling in different directions, so you also have to account for that when trying to determine what the actual buckling load of the system is.